Our solar system is an impressive collection of celestial bodies, ranging from giant gaseous planets to small, rocky bodies. Each component has its own quirks and mysteries, making it a subject of ongoing study for scientists and astronomy enthusiasts. This complex system offers a fascinating insight into cosmic dynamics and the processes that have shaped the planets and other celestial bodies over billions of years. Exploring the solar system has revealed much about the formation and evolution of planets. Through space probes and powerful telescopes, scientists have been able to unravel many of the secrets these celestial bodies hold. However, each new discovery brings new questions, keeping alive the quest for knowledge about our place in the universe. Venus is one of the most intriguing planets in our solar system, known for its extreme and mysterious conditions. With a dense atmosphere and surface temperatures that can reach over 450 degrees Celsius, Venus is truly a hellish environment. These characteristics make Venus a fascinating study subject for scientists seeking to understand how planets can evolve under such extreme conditions. In addition to its scorching temperature, Venus also features crushing atmospheric pressure, about 90 times that of Earth. These extreme conditions offer a glimpse of how the most hostile environments can exist in our own cosmic backyard, raising important questions about habitability and planetary evolution. Studying Venus can provide valuable insights into the processes that may occur on exoplanets with similar conditions. One of the most intriguing features of Venus is its retrograde rotation. Unlike most planets, Venus spins on its axis clockwise, a phenomenon that challenges conventional explanations and suggests a violent and turbulent history. This unique rotation has been the subject of many theories, including the possibility of a colossal impact that could have reversed its rotational direction. This retrograde rotation is not just a curiosity, it has profound implications for the planet's atmosphere and climate. The interaction between Venus's rotation and its dense atmosphere results in climate patterns and winds that are unlike any other planet in the solar system. Understanding these dynamics can help scientists develop more accurate models to predict atmospheric behavior on planets with extreme features. The formation of planets in our solar system is a fascinating process that began about 4.6 billion years ago. This process started when a cloud of gas and dust, known as the solar nebula, began to collapse under its own gravity. As the nebula collapsed, it spun faster and flattened into a disk, with the sun forming at the center and the planets forming from the remaining material of this disk. Uranus stands out in our solar system for its extreme axial tilt, with its rotation axis almost parallel to the plane of its orbit. This unique tilt, about 98 degrees, makes Uranus appear to be lying on its side as it orbits the Sun. Scientists believe this unusual orientation is the result of a colossal collision with a planet-sized object early in Uranus's history. Due to its extreme axial tilt, Uranus undergoes dramatic seasonal changes. During the summer solstice in one hemisphere, the pole tilted toward the Sun experiences continuous sunlight for 42 years, while the other hemisphere remains in darkness. This alternation of lighting creates radical climate variations between the hemispheres, with profound effects on the planet's atmospheric dynamics. The orbital tilts of planets in our solar system have profound implications for the environmental conditions they can support or challenge for life. For example, Uranus's extreme tilt results in radical temperature variations between its hemispheres over its long year, drastically altering the atmosphere. This phenomenon shows how minor variations in a planet's orientation can result in significant climate changes. In addition to Uranus, other planets also exhibit orbital tilts that influence their climates. On Earth, The tilt of approximately 23.5 degrees is responsible for the seasons. Subtle changes in tilt over time can cause extreme climate variations, such as ice ages. These insights are crucial for understanding not only Earth's climatic past, but also for predicting conditions on exoplanets that might harbor life, expanding our understanding of habitability in the universe. Tidal locking is a phenomenon where a celestial body always shows the same face to the object around which it orbits. This effect occurs due to gravitational forces that synchronize the body's rotation with its orbit. A classic example is our Moon, which is tidally locked with Earth, resulting in the same face always facing us. This phenomenon has significant implications for the dynamics and climate conditions of celestial bodies. Planets and moons tidally locked may have one side permanently facing their host star, resulting in extreme climatic extremes, one side blistering hot and the other in freezing darkness. The unique conditions created by this locking can affect the atmosphere and the potential habitability of these bodies, making them interesting targets for study. The Moon has played a crucial role in the evolution of Earth. Its presence stabilizes Earth's axial tilt, which contributes to a relatively stable and predictable climate. Without this stabilization, Earth could experience drastic variations in axial tilt, resulting in extreme and unpredictable climate changes over millions of years. Additionally, the Moon influences the tides on Earth, a phenomenon that has a significant impact on coastal ecosystems and marine life. Tides also play a role in global ocean circulation, affecting the planet's climate. Understanding the interaction between Earth and the Moon is essential for studying how gravitational forces shape planetary systems and how they can influence habitability on other worlds. Pluto and its largest moon, Charon, present a fascinating case of mutual tidal locking. Both bodies are locked, always showing the same face to each other. This phenomenon creates a unique gravitational dance that allows scientists to study the effects of gravity in binary systems in detail. The relationship between Pluto and Charon challenges the traditional understanding of planets and moons. Instead of a moon orbiting a planet, both orbit a common point in space, known as the center of mass. This system provides an interesting model for studying orbital mechanics and tidal forces in a context where the bodies are comparably sized, offering insights into the formation and dynamics of other stellar systems. The gas giants of our solar system, Jupiter and Saturn, are known for their enormous masses and complex atmospheres. Jupiter, the largest planet in the solar system, has an extremely fast rotation, with a day lasting less than 10 Earth hours. This rapid rotation contributes to the formation of prominent atmospheric bands and the iconic Great Red Spot, a storm larger than Earth that has persisted for centuries. Saturn, famous for its spectacular rings, also has a rapid rotation that influences its atmosphere and internal structure. The centrifugal force generated by the rapid rotation of Jupiter and Saturn leads to a noticeable flattening at their poles, distorting their shapes into oblate spheroids. This flattening affects everything from wind patterns to the distribution of their internal masses, providing essential data for models of how gravity acts on massive bodies. The rotation speeds of planets have profound implications for their atmospheres and internal structures. The rapid rotation of Jupiter and Saturn, for example, results in significant centrifugal force affecting the shape of the planets, causing flattening at the poles and a widening at the equator. This oblong spheroidal shape influences the distribution of internal mass and atmospheric patterns. In addition to shaping the physical structure of planets, rotation speeds also affect their atmospheres. In Jupiter, the rapid rotation contributes to the formation of distinct cloud bands and storms like the Great Red Spot. These dynamic atmospheric patterns are an area of intense study, as they offer insights into planetary meteorology and the climatic processes that may occur on other giant gas worlds. Venus and Uranus exhibit rotational anomalies that distinguish them from other planets in the solar system. Venus has an extremely slow retrograde rotation, with a day longer than its year, spinning clockwise, unlike most planets. This peculiar rotation is a puzzle that intrigues scientists and suggests that Venus may have undergone cataclysmic events, such as significant collisions, that altered its rotational dynamics. Uranus, on the other hand, rotates almost sideways, with an axial tilt of approximately 98 degrees. This unique positioning causes Uranus to experience unusual seasonal extremes and raises questions about the planet's impact history. Studying these rotational anomalies helps us understand how significant events can profoundly alter the rotation and evolution of planets, providing valuable insights into the formation and dynamics of planetary systems. The Sun, the central star of our solar system, exhibits an intriguing differential rotation. The solar rotation is not uniform. The equatorial region spins faster than the polar regions. This phenomenon occurs due to the fluid nature of the Sun, where plasma at different latitudes moves at varying speeds. Differential rotation is essential for generating the solar magnetic field and for the dynamics of sunspots. The formation of the solar system is a fascinating story that dates back approximately 4.6 billion years. The most accepted theory is that it formed from a solar nebula, a gigantic cloud of gas and dust that began to collapse under its own gravity. As the nebula collapsed, it spun faster and flattened into a protoplanetary disk, with the Sun forming at the center and the planets and other bodies clumping together from the remaining material. This formation process is a classic example of the conservation of angular momentum, a fundamental law of physics that applies on cosmological scales. As the nebula collapsed, angular momentum was conserved, leading to the rotation of the planets that formed. Studying the formation of our solar system not only sheds light on our own origin, but also provides valuable insights into the formation of other planetary systems in our galaxy and beyond. In the center of this disk, the material clumped together to form the Sun, while particles of dust and gas collided and merged to form planetesimals, which are the building blocks of planets. This accretion process continued, eventually forming the planets, moons, and other bodies of the solar system. Studying the solar nebula and gravitational collapse helps us understand the fundamental processes that shape the formation of planetary systems. Exoplanets are planets that orbit stars beyond our Sun, and their discovery has revolutionized our understanding of the universe. Through space telescopes like Kepler and TESS, scientists have identified thousands of exoplanets, many of which possess characteristics that challenge our expectations about the types of planets that can exist. Some of these worlds have conditions that may be favorable to life, increasing our curiosity about the possibility of extraterrestrial life. The diversity of the exoplanets discovered is astounding. There are super-Earths, gas giants, and planets in habitable zones that could have liquid water on their surfaces. Studying these exoplanets not only expands our understanding of planetary formation and evolution, but also helps us identify the best candidates in the search for life outside the solar system. Each new discovery brings valuable insights into the complexity and diversity of the worlds that exist in the universe. The search for life on exoplanets is one of the most exciting frontiers in modern astronomy. Scientists are particularly interested in exoplanets that orbit within the habitable zones of their stars, where conditions might allow for the existence of liquid water, an essential ingredient for life as we know it. Advanced telescopes like the James Webb Space Telescope are equipped to study the atmospheres of these exoplanets for biosignatures, such as oxygen and methane. The discovery of potentially habitable exoplanets has raised the expectation that we are not alone in the universe. Beyond the detection of biosignatures, future missions may include probes that travel to nearby stellar systems to directly investigate these distant worlds. The search for life on exoplanets not only helps us better understand our own planet, but also expands our perspectives on life in the cosmos. Recently, the detection of phosphine in the atmosphere of Venus has sparked significant scientific interest. On Earth, phosphine is associated with biological processes, raising the hypothesis that there could be forms of microbial life in the upper layers of Venus's atmosphere. These layers are significantly milder compared to the scorching surface of the planet, making them an intriguing area of study. The presence of phosphine on Venus challenges our current understanding of the environments where life can exist. To investigate further, future missions might send probes to collect atmospheric samples and directly analyze the compounds present. This finding not only elevates the possibility of life on Venus, but also broadens the search for biosignatures in other worlds of our solar system and beyond. The discovery of exoplanets has revealed a surprising diversity of worlds, many of which challenge our existing categories and understandings of planets in the solar system. Planetary systems with configurations very different from ours suggest that the processes of planetary formation can be more varied than previously thought. Many of these systems feature exoplanets in orbits extremely close to their stars, or with masses that challenge our expectations of what constitutes a giant gas planet or a super-Earth. These findings are important because each new system discovered provides valuable data on how planets can form and evolve in different stellar environments. Studying these systems helps us better understand the potential for life in environments that, at first, might seem inhospitable or unlikely. The diversity of exoplanets expands our horizons and challenges the existing models of planetary formation. Super-Earths are planets that have masses greater than Earth's, but substantially smaller than the gas giants of our solar system. These planets offer fascinating conditions for study due to their varied compositions and potential habitable environments. Some super-Earths may have dense atmospheres, deep oceans, or even geologically active conditions, providing a range of environments that could support forms of life. Investigating these worlds is complex and requires advanced technologies to determine their atmospheres and surfaces. However, the effort is worthwhile, as it may reveal whether life is possible on scales and conditions very different from those on Earth. The discovery and analysis of these super-Earths also play a crucial role in assessing the viability of future colonization or mining missions, expanding our possibilities for the future of space exploration. The era of space colonization is closer than many imagine, driven by rapid technological advancements and renewed interest in outer space. Private companies and government agencies are investing in space travel technologies, orbital habitats, and more efficient life support systems. The dream of establishing human colonies on other planets is becoming increasingly tangible. In addition to ensuring the continuity of the human species, space colonization offers a unique opportunity for scientific research in completely new environments. Experiments in biology, physics, and other sciences in microgravity or extraterrestrial conditions could lead to discoveries that would be impossible on Earth. The creation of habitable infrastructures on other planets will also drive innovations in areas such as environmental engineering, robotics, and bioengineering. Interplanetary travel represents one of the greatest technical challenges for space engineering. Overcoming the vast distances, the harsh environmental conditions of space, and the effects of space radiation requires innovations in propulsion and materials, as well as a deep understanding of human physiology in long-duration space environments. Developing spacecraft capable of safely transporting humans between planets is an active field of research. Potential solutions to these challenges include nuclear propulsion, hibernation systems for crews, and advanced radiation shields. To make interplanetary travel a practical reality, it is necessary to develop support infrastructures, such as refueling stations in orbit and bases on other planets. These structures will serve not only as stopovers for future missions, but also as research and development centers for the continuous exploration of the solar system. To sustain space exploration and the colonization of other planets, building support infrastructures is essential. Orbital space stations, like the International Space Station, already provide a model for human habitats in space, but future interplanetary missions will require significant advancements. Lunar and Martian bases are the next logical steps, offering locations for refueling, research, and life support. These infrastructures require advanced technologies in areas such as solar energy, water recycling, and indoor food production. Additionally, the use of local resources, such as extracting water from Martian ice, will be crucial for the sustainability of these bases. The development of these technologies and infrastructures not only facilitates space exploration, but also drives innovations that can benefit life on Earth. Adapting vehicles for operation on other planets is a complex task that requires a deep understanding of planetary environments. On Mars, for example, dust storms and the thin atmosphere require vehicles with robust traction and advanced air filtration systems. Each planetary environment, from the high temperatures and pressures of Venus to the ice and radiation of Jupiter, presents unique challenges that must be overcome through innovative design and adaptive technology. The design of such vehicles not only focuses on functionality and survival in extreme conditions, but also on energy efficiency and the ability to conduct scientific research. This includes the integration of data collection systems, analytical tools, and, in some cases, autonomous systems that allow for independent exploration of areas that would be inaccessible or dangerous for humans. Vehicles like the Martian rovers are examples of how technology can be adapted to explore new worlds. Mars has been the main focus of space exploration due to its relative accessibility and potential for human colonization. With the discovery of liquid water beneath its surface and the similarity of its day and seasons to those of Earth, Mars represents the most viable candidate for the first extraterrestrial human colony. Programs like the Mars rover and planned manned missions are paving the way for this eventuality, studying the geology, atmosphere, and potential agricultural capability of the planet. We bring you an incredible series of videos like this one. Subscribe to our channel so you don't miss out. The colonization of Mars will require advancements in many technologies, including life support systems, sustainable habitats, and methods for utilizing local resources and processes such as manufacturing building materials and producing water and oxygen. Each mission to Mars brings new data that helps us better understand how to prepare humanity for living outside Earth, and each success brings us closer to a multi-planetary future. Space exploration is more than a quest for scientific knowledge. It is also an expansion of human frontiers. As we look beyond Mars to other destinations in the solar system, such as the enigmatic oceans of Europa or the rich atmospheres of Titan, we face challenges that require new technologies and ways of thinking about our own existence and our place in the universe.